All right, so my name's Jacob.
I'm Everett,
And I'm Warren.
and we studied aeronautical engineering at the University of Colorado Boulder.
And also mechanical engineering.
Yeah.
That's what I did. So the overview, we were at Boulder, and our mentor was Andrew DeHere. He's in the crowd right there. Great guy. It was, yeah. It's very hot. We
Yeah.
live here, and we weren't ready.
And our
Very
first
hot.
day there, we showed up in our pants and our thick collared shirts, and it was 99 degrees. And that was the day he gave us the tour of the entire campus.
Yeah, so we walked from like the lab outside of campus all the way to campus, and we kind of died that night.
Okay, so one of the facilities we worked at is called LASP. That is the Laboratory of Atmospheric and Space Physics.
And so it's a research organization associated with CU Boulder, and it gets funded from NASA.
And so we ourselves didn't do much of our research there. That was mainly for Andrew and his colleagues. They had a TVAC chamber, which is a temperature vacuum chamber. That's where they did tests on the actual satellite that we were working on.
And that was the TVAC
But
chamber.
we worked in a smaller labs in our offices, which we'll get to soon.
So this is QB50. We were working on small cube satellites. And so it's like only about like that big.
It's 2 U's, and a U is 10 centimeters by 10 centimeters by 10 centimeters. So this one is 10 centimeters by 10 centimeters by 20 centimeters. And so it's just basically a small satellite that they are sending up into orbit. It's going to take measurements with a science instrument, and the science instrument is the hockey puck looking thing on the end.
And there. Bye. Yeah. And so this is the QB50 lab. This was inside of the engineering center at the university. And so down here, we're all wearing these little lab coats. They're called ESD coats, and they protect from electrostatic discharge, so you don't arc the solar panels or any electronics you're working with that would destroy the panels.
So we had offices on campus, which was like super cool. We had little cubicles, and that was fun.
Yeah.
That's where we did most of our work. We occasionally went down to the lab, but whenever we came in, we'd come into these offices, spend a few hours working at our desks, and that was pretty much it.
So we all had like our own individual projects while we were there, and mine was doing tests on the flight batteries of the CubeSat, and the flight batteries are the actual batteries that will be going into space. So for the beginning of my project, I was debugging this code right here. We couldn't get it to recognize the correct capacity that was coming into the batteries, so I had to write a different code for the charge and discharge cycles so that we could get the correct data. And so this is charging. We hooked up the flight batteries to the DC power supply, which is that big thing up there. And we ran it through this little computer chip called an Arduino, which is what took in the data and put it onto my computer so that I could use it later. And discharging, we couldn't discharge it through anything electronic because we didn't have anything big enough. So we used a variable ohm resistor, and we put it to 8.4 ohms so that we could discharge at 1 amp. And so that took a really long time to discharge. It took like 24 hours every time, so that was kind of a pain. And so in the end, my best data that I collected was the voltage versus capacity while discharging the batteries, and that's what's going to be able to create the estimation for the state of charge of the batteries while they're on the CubeSat.
All right, so my objective was to make a model of the Maxwell satellite. The Maxwell satellite is bigger than QB50. It is 6U, so that means that there's 6 10 by 10 by 10 centimeter squares, if you will, like that make up it. So this is Maxwell. Step one, I had to figure it out piece by piece. So I had someone who had already modeled it on their computer send me all the parts, and I went through everything and decided how best model it like in person, physically. So it was decided that the 6 walls I would laser cut, the antennas I could laser engrave, and then I would do the solar panels also laser cutting and laser engraving. And then the inside components I made out of styrofoam, so it was super simple. And the only thing I had to 3D print was the feed horn. So the next step was to go to the ITLL. That is the Integrated Teaching and Learning Lab. I think it's the coolest facility on Boulder's campus. They have some super cool machines like the laser cutters and the 3D printers. And that was super fun. I had to get taught how to use everything. And that was super simple, only took a day, and then I could really start. So there's a laser cutter. They're pretty cool. I learned how to use that. Yeah, they're the same kind. Yeah. The software I used for that was Corel. It's a CAD software. And that was pretty easy. I just had to remake all of the panels, which are just rectangles. So I learned a ton about CubeSats, and my SolidWorks skills greatly improved. I was pretty proficient in 3D modeling, but on Autodesk Inventor Pro. So SolidWorks was new to me, and I'm glad I learned it because most companies use it. And also I learned to heed the 60-second laser cut warning, because if you open it too soon, you breathe in melted acrylic. That sucks. You got a wicked headache. So I got patience from this. And the outcome overall, I think my project turned out quite well. My mentor actually took the model that I made to, where was it, like the Netherlands? Yeah, Small Sat conference, and they loved it. We were the only ones with a physical model, so let's go. And yeah, it was cool.
All right.
Yeah. What's up, Everett?
I get applause.
So my project was a solar array simulator. I basically had to write a program that would simulate the outputs of solar panels on the satellite at different angles of sunlight. And I coded this in Python. And yeah, I used an Agilent E4350B solar array simulator. And this is the actual simulator. I would connect to the back panel with that there USB GPIB cable. So I'll show you the back panel. So I'd connect to the GPIB port right there in the left picture, and it had a cord that would connect to my USB port. And this thing was a fickle beast. It really only worked when it wanted to work, and it weighed nearly 70 pounds. And I had to carry it up 2 flights of stairs to our offices from the lab in the basement. So this was most of my code. I couldn't fit all of it, but basically it took me nearly 300 lines of code to finally get this thing working. And I actually did get it working like the second to last day of my internship, which was pretty satisfying. And so overall, I finally got the program to finally function properly. And my knowledge of circuits, electricity, and coding has grown. And I'm proficient in a whole new topic of Python, which I teach myself, which was pretty cool. And so our thanks go to Andrew DeHeer, Sarah Holbrook, LASP, CU Boulder, and yeah. And for future pin turns, I'd say just go for it. It's a lot of fun, especially if you can go with your friends. And yeah, you'll learn a lot and ask questions, and can't lose anything, so just apply.